Next one, exercise 6.1 about derivative. Well, this is, as I told you before, simple differential calculus we are concerned with. So we have functions of just one independent variable called x. But on the other hand, as you see, I decided to choose some, well, basically here I decided to choose a rather exotic function, which many people never encounter because they are somehow well familiar with polynomials, sort of x power 3 plus 5 times x power 2, etc. So that the exponent is a constant and often whole number. This is nice, and we all know that there are certain simple differentiation rules for those cases, even if we have fractional or even irrational exponents, things like that. On the other hand, we know expressions like e power x or generally speaking, the general exponential function a power x, things like that. And also there we have quite simple differentiation rules which we can always apply. Now the problem is that encountering the term x power x, so x to the power of x, at first sight it's not immediately clear what it is. Is it an exponential or is it a polynomial? Now, you could say it's neither nor, but if you have to decide, you should clearly decide it to be an exponential term instead of a polynomial, because I can promise you that at least on the long side, on the long run, the growth of values, of function values of this term is much, much higher than of any polynomial. And the reason is easy. The reason is that the exponent increases with the independent variable x. And you could say it's even stronger than something like e power x, because the basis, other than the exponent, additionally to the exponent increasing, even the basis increases with x. So it seems to be sort of a super exponential function, and that's what it is. That's what we call it. It's a super exponential function. And now our business is to transform this expression in such a way that we find something which we can apply our well-known differentiation rules to. And these well-known differentiation rules are quite handsome. You know, it's not so, there are not many of them. We have some simple things like additional constants go away when differentiating, constant factors stay alive, they just stay as they are. Then we have our product rule, ratio rule, and chain rule, and that's it basically. But now let's bring this into a form where we can proceed. Now this is, you could say this is a very famous trick often applied to exponential expressions in cases where you just don't get along without, right? So this is a question of finding the right step. Now, just follow me. It's always possible to take this term as it is and fill it into the expression e to the power of ln of something. You see what I mean? If I say e to the power of ln, these are two operations which cancel each other. Yeah, so exponent, yeah, you could say exposing e to the power of ln of something means that you apply the famous exponential function, but in the next step you apply its inverse function. Let's take an example. If I say e to the power of ln of 2, so roughly speaking, what remains is simply 2, because it's just the fact that, on the other hand, if I have an equation e to the power of x equals 2, to find x, I would have to apply the natural logarithm to this expression, which gives me the exponent. So x would be equal to ln of 2. And now if you compare these equations, you find that it's exactly true that in this upper case, the result must be 2. So what it means is, in the end, that e to the power of ln of something, this double operation cancels itself. So you can just cross it out, and what remains is your argument here behind. I hope you understood this, because this is just a simple trick very often applied to exponential expressions, which always works. Now look what we get. We get e to the power of ln of what we have, and what we have is x power x. Now we can apply the famous third rule of logarithms, where you remember that we are allowed to take the exponent inside here of the argument, to take it as a factor, which means we just pull it before the ln. This is a very famous general rule which states that any logarithm, no matter which base, of a power b equals e times logarithm of a. So this is well known. We've used it before, and I hope I don't have to explain it again. So this, please don't mix it up with the corresponding differentiation rule for power functions, for polynomials, which is similar but different. Okay, so then what we get is here in the exponent we get x times ln of x. Now this is something we can work with. Why? Because this is a sort of a modification. Well, it's a modified version of the exponential function, where the argument is no more x alone. Instead, it's the composite expression x times ln of x. And that's a case clearly for the famous chain rule of differentiation. So what I do is I take the derivative by saying this is an exponential. So the outer function in this nested expression is x is e to the power of something, and we know that the derivative of e power something is still e power something. So we just you could say we just leave this alone, this exponent. We just say e power x times ln of x is the derivative, but we must, of course, account for the fact that the exponent is not x alone. Instead, it's some expression of x, and the chain rule has been designed exactly for this purpose, in order to account for the inner function. And the method, or you could say the step we have to take, is thankfully easy. It just means we have to, in German we say nachdifferenzieren. So we just have to multiply the inner derivative to our outer derivative, which we just put here, right? So we have to multiply the derivative of the exponent term, which now look, this is a case again for the product rule of differentiation, which tells us we have to differentiate the first factor, x differentiated for x gets 1, leave alone the the other factor, which is ln of x, I put it here, then plus the other way around. The other way around means leave this first factor alone, just put it there, x, and then take it times the derivative of the other factor, and we all know that the derivative of ln of x equals 1 over x. And so what we get, this is even nicer, because this shortens to be just 1. What we get equals this, well, this transformed expression e power x times ln of x, but then times, in parentheses, ln x plus 1. And you see, this was just our trick to transform this x power x to be this one, in order to get things done. But now we can draw back this transformation and go back to the original notation of x power x. And the interesting result is that this function has the same, basically the same feature as any exponential function, namely that it appears in its own first derivative, but we have an additional so-called growth factor, which is in this case even increasing while x increases. So you might have found something similar, sort of ln a with a general exponential function. Anyway, so this is the result that this is a function which has striking similarity to the growth behavior of other exponential functions. Well, after all, this is a remark just for you to know, because it's really an interesting function. It's quite surprising that this function x power x has a graph which looks roughly like this one. It has the feature that at first, and in the region of low positive numbers, where we, well, I must say that you should be careful and say here, definition, well, domain should be real numbers positive, perhaps including the zero. Zero is a critical case, but it's possible. But please don't apply it to negative numbers. You might try and do so, but you will get problems. Don't ask me. You get many problems if applying this to negative numbers. Just remember, taking a certain root of a negative number, we don't want to go into the complex domain here. We want to stay real with real numbers. So it's a good idea to restrict the domain to this one. Now, then two interesting effects are, there is an absolute minimum to this function, which turns out to be positioned at x equals 1 over e. We can even easily calculate this absolute minimum value then of this function. Now you see here, this is easy. We just insert 1 over e into the term, so we get 1 over e power 1 over e, which is, in other words, the reciprocal of the eth root of e. So this sounds pretty cool, and it is actually. It's a number around, oh, I forgot it. Well, something below 1. Not so interesting, perhaps. But the fact that there is a minimum, and only then the graph keeps growing and growing. Okay, so the function shows the usual behavior of an exponential. This is quite interesting. The other interesting thing is that, again, using the rules of L'Hopital from before, it's possible to show, using this function, if x approaches 0, it's possible to clearly show that 0 to the power of 0 must be 1. Instead of 0, some people would expect that 0 to the power of 0 must be 0. It's not. It's equal to 1. This can be shown with limit methods. We will not do so here. This was just an exercise for simple application of differentiation rules, and the second one is about a modified logarithmic function. Here I give you all the 3 logarithmic rules again as an overview. You see, the first one is about product argument, the second about a fractional argument, where you can split it up into the sum of 2 logarithms here and the difference of 2 logarithms here, while the third one is the one which I just used before, taking the exponent as a factor, extracting it here and putting it there. So that's well known. Now we will possibly need one or more of these. Well, I think we will actually be able to use the third one, and in principle even the second one. Let's just look and see. Now, first of all, this term y equals ln of the square root of the fraction 1 minus x squared, this quantity over 1 plus x squared. It seems to be strongly nested. Well, it is, but it's no problem for us to find the first derivative because we have the chain rule available, and the chain rule has the big advantage that it can be applied even for multiply nested functions. So what you do is you just take the derivative from the outside to the inside. You just go through the whole expression. That's all, right? By multiplying. That I call it g of x. And then look here, what I get is, first of all, it makes sense to put to replace the square root sign against an exponent of 1/2. You all know this, because the differentiation rule of exponent expressions is very well known, or what I mean is about power functions, right, with a constant exponent. So what do we have? We have the ln of some parenthesed fraction to the power of 1/2. We take the derivative from the outside to the inside. So we start out recognizing, let me see, is that true what I'm saying? No, I just see that, yeah, right now. Okay, you might, and you are officially allowed to do so, you might just start differentiating step by step and so on. But before I start differentiating, I recognize that this is a logarithmic expression which may be simplified by the use of these logarithm rules. So this is at least a good idea to simplify terms before differentiate. It's not it's not an obligation. You may do so, you may not. The very interesting thing is that either way, if differentiating right away, or first transforming then differentiating, or even transforming twice and then differentiating, in all these cases you will find one and the same first derivative, which is this one, which is here, this simple fraction. So that's again, that's a nice thing to know, that mathematics guarantees us to be consistent, so that the logarithm rules are completely consistent together with all our differentiation rules, which is a little bit a surprise, because we never asked for that. We're just happy to find that mathematics is consistent. It would be nice if it were complete also, but sadly speaking, it never can be consistent and complete at the same time, which was proven by the famous Kurt Gödel, as you know, Gödel Unvollständigkeitssatz, incompleteness theorem, etc. But this is not our topic, okay? So what I do is the following. I replace the square root sign by an exponent of 1/2. Then I use the third logarithm rule by pulling this exponent as a factor 1/2 before the logarithm. Now, this is really, I'm happy, because it means that my differentiation effort will be less due to, I got rid of the square root sign, you see. Then I have a fraction here, and I remember, oh, there is this second logarithmic rule even, where I must be a little careful, honestly, should be careful in the case of a and b getting negative at the same time. Then this fractional way of taking the logarithm would still be well defined, the other terms would not. But here we have a denominator which is strictly positive, so everything's fine, shortly speaking. And so we may even go a step further and say that the ln of this fraction equals the ln of the numerator minus the ln of the denominator. So that's a simplification of terms in 2 steps, where I get 1/2 times, now in brackets, ln of parentheses 1 minus x squared minus ln of parentheses 1 plus x squared. And that's a nice expression to start with in order to find the first derivative. Let's do so. Well, I leave this factor of 1/2 alone, it stays there. I take the outer derivative of the natural logarithm of its argument, which is always the reciprocal of the argument, right? So I get 1/1 minus x squared. But then, don't wonder why this is here. Then I have to use the chain rule to multiply the inner derivative. And the derivative of this inner term, of course, is 1 goes away. Negative x squared gets differentiated to negative 2 times x. So that's why I put it in the numerator here. Next step, minus, and the same procedure again. I take the outer derivative, the derivative of natural logarithm of ln equals the reciprocal of its argument. So I get reciprocal of 1 plus x squared. And then I have to take the inner derivative again due to the chain rule. 1 goes away, 1 disappears, and plus, but the x squared gets differentiated to be 2x. That's all. And now I have 2 fractions inside, which I can easily combine. Also, I might just draw these common factors outside. You see what I'm doing? First of all, well, I could even here, I could cross out the factors of 2 against this 1/2. So in the end, there will be no additional factors. But then also I decided to take a negative sign outside. You see here it's minus, and here it's a minus sign. I can pull this outside together with the x, and then what I get nicer, a little bit nicer than before, oh sorry, will be Is it? Here will be minus x times, and then I have my positive fractions. Well, I have positive expressions here, 1 over 1 minus x squared plus, you know, because I drew the minus sign outside, plus 1 over 1 plus x squared. And now these two fractions may easily be combined to be, you see these two terms are quite different, so I just multiply them, and then but I expand these fractions with the crossover method, right? So that I put the 1 plus x squared factor in here, and you know what I mean. So I just make a crossover expansion of these fractions in order to put them on a common fraction line. And then here I get, on the left-hand side, I get 1 plus x squared, and then I get plus the other one, namely 1 minus x squared. And then I can remove the parentheses. I see that 1 plus 1 remains to be 2. I see that plus x squared actually cancels out against negative x squared here. So a simple 2 remains in the numerator, but this outdrawn factor of negative 1 may be pulled up again. So I get negative 2x here. And below, this is nice, because due to the third binomial formula, I should say binomic, I must look it up, okay? Due to the third binomic formula, this is sort of like a minus b multiplied with a plus b, resulting to be a squared minus b squared. Using this scheme, I get 1 minus square of x squared, so 1 minus x power 4. And even nicer, I can take away this minus sign by exchanging the denominator terms, and so I get 2x over x power 4 minus 1. Please take your time for your own exercising purposes and try and solve it once again in two different ways. First, taking this expression as it is and take the derivative right away. You might even leave the square root sign alone and then use that, you know, the derivative of square root of x equals 1 over 2 times square root of x. Sort of this, you don't need to, but you might. Check it out, then do this transformation step and start differentiating from this point and compare your results every time with my result here. You will always get the same result. So that's quite interesting to find. Here, as just an addition for your interest, here you see the graphs of these two functions. In gray color, you see the famous x power x function here, and also its first derivative. So you may see that actually there's a 0 of this resulting first derivative here, which I get, since this can never be 0, this one must be 0. So I get ln of x equals -1, and then solving for x, I get x equals 1 over e. That's what I told you before. So this is the proof that there's an absolute minimum in the end at 1 over e. So it's quite convincing to see that the green curve represents the, well, you know what it is. It's the, it gets you the values of the slopes of all the tangents of the gray curve. That's what the first derivative tells you. And the same holds for this modified logarithm curve, which you see in green color here, this g of x, and its derivative, this fraction function, is quite interesting also. It has a 0. It goes to the origin, of course, because obviously the green curve has a horizontal tangent at this position. So everything's consistent here. That's nice to know. Thanks.